Here it is much colder than I expected, and I think I caught a cold just right after I arrived here. So, but I feel sick a little bit, but I try my best in the presentation. Okay, so today I want to talk about 3 items here. One is the spin pumping in ferromagnet, antiferromagnet bilayer system. And our very recent result about the terahertz spin pumping in the antiferromagnet, and also our effort on the fabrication of chiral antiferromagnets, manganese 3 iridium. Okay, so why we do antiferromagnet spintronics? I think we don't have to explain in detail, but a small susceptibility and a no stray field maybe enable us to make this very high dense memory. And also the high frequency terahertz dynamics may be opening up the terahertz spintronics. I'd like to talk a little bit about these terahertz things in this talk today. So when we started this antiferromagnet spintronics, the very basic fundamental question is how the spin current interact with the antiferromagnet. So in the ferromagnetic case, it is very well known. When we inject a spin current into the ferromagnet, the magnetization feels a spin torque. And when the spin current is large enough, we can flip the magnetization into the other direction. But however, for the antiferromagnetic case, it is not really clear at that moment. However, in the very simple model about this macro spin model, actually we can write the equation. So for the ferromagnetic case, it is well known that a spin torque can be written in terms of this double cross product. So and then we can assuming this relative angle between the magnetization and the spin polarization to be theta, we can rewrite this equation to be sine theta squared. Actually, in the antiferromagnetic case, in a strong exchange limit, we can actually write in the very similar manner using a Neal vector I in this case, where Neal vector is a sublattice 1 minus sublattice M2 in the vector. Again, when we assume that relative angle between the spin polarization and the Neal vector to be theta, we can rewrite this equation in terms of the sine square theta. So in order to investigate the actual spin torque, actually we can, from here, we can actually, in this picture, we can see a spin torque as in the spin current point of view. This is like a spin dissipation. So we can just characterize the spin dissipation to characterize the spin torque in the antiferromagnet. So what we do to characterize the spin dissipation in the antiferromagnet is by using the spin pumping effect. It's a very famous effect where when we have the spin precessing magnetization, can pump the spin current into the adjacent non-magnetic material. Depending on the spin dissipation property in the non-magnetic material, this spin pumped current creates a spin accumulation, and it again creates a backflow current. And depending on this difference between the spin pumping current and the backflow current, it will give a damping. Damping enhancement. So by looking at this damping enhancement, we can somewhat characterize the spin dissipation property in the non-magnetic material. So the very famous experiment, it's a typical experiment is done by the Mizukami and the co-workers in a very long time ago using copper as an adjacent material. And they see the Gilbert damping decrease as the copper thickness increases. So by using this equation, they are able to characterize the spin diffusion length of the copper to be 250 nanometers. So what we have done is basically just replacing this non-magnetic material to the antiferromagnetic material. So again, just excited dynamics and pump a spin current into the antiferromagnet. If the spin current dissipated in the antiferromagnet, damping change should be observed in the ferromagnetic material. From there, we can kind of say that there is a spin torque effect in the antiferromagnet. So the first, we did a very similar experiment to the very previous copper experiment. So we just put the iron manganese antiferromagnet and then vary the thickness of it. And then we characterize damping alpha here. So again, damping decrease as we increase the iron manganese thickness. So by using this equation, we can somewhat characterize the spin diffusion length of the iron manganese to be 100 nanometers. This is very similar to the previous work. And again, so this spin diffusion length seems to be very long, but we may be able to explain this long spin diffusion length by the spin current carried by the spin fluctuation or spin wave or magnon. The other thing we can do for the antiferromagnet is because it's changing the antiferromagnetic order. So say right now it's all aligned in the ferromagnetic moment direction. But what happens if we twist the antiferromagnetic order? So based on this spin torque equation, we should observe the additional damping enhancement. So what we have done is, again, this is iron manganese permalloy bilayer. We just create an exchange bias in the certain direction. And when we measure the Gilbert damping, by the way, the Gilbert damping is measured by the ferromagnetic resonance and the character the linewidth, and from that we can measure damping. So for the measurement, we just apply the external magnetic field by relative angle phi, and we just take the Gilbert damping as a function of the relative angle phi. So as you can see, in some iron manganese thickness, we have enhancement around 180 degrees, where the twisting is maximized. So when we take this delta alpha here and then compare with exchange bias field, iron manganese thickness dependence of the exchange bias field here, actually this delta alpha here is kind of linearly correlated with the exchange bias field. So this means that the more exchange bias field you have, we get more delta alpha, the enhancement of damping, which is consistent with the spin torque picture. So one more thing we can do from this result is because because the exchange bias field can be kind of adjusted by the temperature, device temperature. So the exchange bias is generally decreased toward the blocking temperature. So in this particular device, the exchange bias field can decrease from 80 aerostat to the 0 aerostat in like 100K. So if you look at this device damping, actually the damping is reduced much. So this reduction is more than half the drop. So this is very kind of beneficial for Spintronic device where Joule heating is involved during the operation, like STT MRAM. So when we write it MRAM, we need to apply the large amount of current. So it will create a heat. At this writing current, we can have the small damping. Therefore, the critical switching current should be reduced. Okay. So the next topic is antiferromagnetic resonance. So recently, we introduced this broadband CW frequency domain terahertz spectroscopy in our lab. So now we can characterize the transmission absorption. We can do the transmission absorption measurement for the bulk antiferromagnetic material, not the thin film, unfortunately. We are working on that. But. So the typical nickel oxide spectra is like this at the room temperature. As you can see, at 1 terahertz, we have a very sharp absorption. And from the line width, we can characterize damping to be like 10 to the negative 4th, which is consistent with previous report. So for this antiferromagnet, there's no point applying a magnetic field. Means even if we apply the magnetic field, not much change in the resonance frequency. So instead, we just change the sample temperature and then measure this resonance. And from this data, we can actually extract the intrinsic resonance frequency of the nickel oxide as well as the near temperature. So from by using this setup, we actually did an antiferromagnetic spin pumping experiment. So here, the sample we have is nickel oxide platinum granular pellet of the thickness 3 millimeters, and we just vary the composition of platinum from 0 to 10%. And we just scan the frequency ranging up to 2 terahertz, and no magnetic field applied. So again, the spin pumping picture for the antiferromagnet is very similar to the ferromagnetic case. And the damping was determined by the line width here by using this equation. And then damping enhancement, delta alpha, turns out to be very similar to the ferromagnetic case. Using this parameter mixing, so-called mixing conductance. Okay, and the S is nickel oxide platinum interface area, and the V is the volume of nickel oxide. So first, we did a characterization of this platinum nickel oxide granular pellet. So the X-ray diffraction and also the polished surface, microscope images of polished surface of this sintered nickel oxide granular basically tells us that there's a very clear interface between the nickel oxide and the platinum, and also nickel oxide and platinum were well segregated. And we also did the antiferromagnetic resonance as a function of the temperature, and then regardless of the platinum composition, we see all the same behavior as a function of temperature. So basically, this tells us that the magnetic properties of nickel oxide are invariant regardless of the platinum inclusion. So the most important part is just characterization of the line width. So we just take the line width here. This peak is right at 1 terahertz. And as we increase the platinum composition, the line width just get broadened. So from this data, we just plot the line width or the damping as a function of platinum composition. So for the control sample, we also create a kind of air granular sample where we have a air pore instead of platinum particle inside the nickel oxide. So as you can see, there's a slight increase, but it's this line width difference is distinct. So from this data, we can say that platinum nickel oxide interface is responsible for enhancement of damping. So in order to model our sample, we just come up with a very simple model where we have the spherical platinum particle in the nickel oxide. And by using this model, we can just rewrite this S over B in terms of the average diameter of platinum and also the platinum composition X. By just fitting our data, we just get mixing conductance to be 43 nanometer -2. So this result, I think, is the first experimental result characterizing this mixing conductance by using a terahertz spin pumping experiment. And then this 43 is actually turned out to be a bit larger than the generally assumed value here for the ferromagnetic platinum case and also the theoretically assumed mixing conductance. Okay. So the third topic is about the chiral antiferromagnets. We recently make an effort to make this chiral antiferromagnets, thin film chiral antiferromagnets, manganese 3X. So the manganese 3X has actually two groups. One is hexagonal, and the other one is FCC. So the most studied one is, I think, is a hexagonal, like manganese tin, manganese gallium. But this FCC type one is less studied. And in fact, for the in the theoretically, manganese 3 iridium has the highest anomalous Hall conductivity, but there's no experimental report. So we just try this material. So the fabrication of manganese 3 iridium film is just by following. So we just make a single layer of manganese 3 iridium 20 nanometer capped by silicon oxide using magnetron spattering and just using arc melted manganese 3 iridium target. And the substrate, what we are using is MgO001 and thermally oxide silicon substrate. And we vary the temperature from room temperature to 700 degrees C. And the characterization, chemical order parameter for the L12 was characterized by the XRD. And the whole measurement, we use a magnetic field up to 24 Tesla. So we just here compare the manganese 3 iridium on the MgO001 substrate and then silicon, thermally oxide silicon substrate. And of course, on the MgO001 substrate, we have the epitaxial manganese 3 iridium because the lattice constant is not that far. However, when we heat up to the 700 degrees C, this epitaxy gets destroyed. However, as you can see, the 001 superlattice peak here, even for the non-epitaxial case, we still can say that we have a L12 ordered manganese 3 iridium. And for the silicon oxide case, we don't have a epitaxial here, but as we can increase the substrate temperature, we start to see the chemical order. Yeah. So we just, okay, so this is a polycrystalline. So we just measure the anomalous Hall conductivity here. So as you can see, we don't see a clear hysteresis opening up to 600 degrees C for the MgO001 case. But at the 700 degrees C, where we have the polycrystalline structure, we start to see a very big opening of the loop. And actually, when we go to the high magnetic field facility to apply up to like 25 Tesla of magnetic field, we can actually see the opening of the hysteresis loop where, for the data which we didn't see any response up to the 9 Tesla field. So actually, this is so the epitaxial film actually required a very high field to see the opening of the hysteresis loop. And of course, for the summary oxide, the iridium 3 manganese on the summary oxide silicon substrate, they are all polycrystalline. So we see the very nice hysteresis curve, and then the anomalous hole conductivity can be go up to 40 inverse ohm centimeter. So to summarize, so we can see this anomalous hole conductivity increase as we increase the substrate temperature, just ignoring this unsaturated value where we need a much higher external field to see the anomalous hole conductivity. And also we see the anomalous hole conductivity, we see the positive correlation between the anomalous hole conductivity and the chemical order parameter. So one thing here is that 40 inverse ohm centimeter is kind of comparable to that have been observed in the manganese 3 tin, but it is an order of smaller, magnitude smaller than the predicted value, which we don't know why. Okay, to summarize, so first I talk about the spin pumping in this antiferro and the ferro bilayer, where we can control the ferromagnetic damping by using the antiferromagnetic order. And then second one is antiferromagnetic spin pumping. We can characterize the mixing conductance. And then last, we fabricate a manganese 3 iridium and then see the positive correlation between the chemical order and the anomalous hole conductivity. Okay, so the I'd like to thank all the collaborators and the co-workers, and also thank the funding sources, and thank you very much for your attention.
So regarding your nickel oxide platinum experiment, I believe the idea is very clever, but so one concern I have is that you only have one single frequency as Portland, which has varied enough to bring it down. But if you only have one frequency, if you were to do the same experiment with the ferromagnet, you could also say that, I mean, extracting dynamical damping, differentiating dynamical damping from homogeneous product is difficult, right? So how can you tell that this is dynamical damping and not just the fact that you are increasing the degree of disorder in some?
So if it's like a simple inhomogeneous damping, we may be just comparing this with this control sample, where you just create inhomogeneity without platinum in the nickel oxide. I mean, this air granular sample where we have the.
You see an increase?
Yeah, but a slight increase. I mean, compared.
It's a different disorder that we're using.
I'm sorry?
So if you take a sample and you mix it with platinum, then right? You will generate different kind of disorders that will lead you to different homogeneous.
Right. Yeah, but I think this is the best we can do. Of course, we cannot really apply field. I mean, we cannot do the similar analysis to the ferromagnetic case, because even if we apply the magnetic field, not much change in the damping and also the resonance field, resonance frequency.
Just a minute. I believe it's a nice experiment. Most likely you've seen spin pumping. The value of the mixing conductance that you extract definitely an upper bound.
Yes.
Valuable.
Yeah, so we can say this is an effective mixing conductance, which might include other effects than the spin pumping effect, like a proximity effect and spin memory effect and so on.
So can you do the same experiment instead of mixing platinum with nickel oxide, just depositing platinum on the back, separated by a little bit of copper maybe, and then increasing distance? That's the other way of doing it, with the single frequency.
Yes, but for this technique, we need a volume. the thin film don't work here. So again, this is the best we can do. And right now, we are also replacing this platinum with something else that has a less proximity effect, considered to be less proximity effect. So from that difference in the result, we might be able to claim something more.
Yeah, a question regarding the magnetic field. I agree, the magnetic field will not shift much frequency, but the magnetic field will be quite effective for the spin pumping. So the principle of spin pumping into the platinum will be quite will be magnetic field, because it makes the two sublattices make symmetry between the two sublattices. So could not be this actually an efficient way to test if it's indeed because of just increasing the order, the disorder, or actually getting really spin pumping. So instead of putting maybe a small inclusion, but putting a platinum film on top of your bulk sample and measuring a kind of spin pump, spin sitting.
I see. But again, this is an effect of like a surface to the volume effect. So if I have like a bulk nickel oxide and just have a single interface between the platinum and the nickel oxide on top, yeah, we don't have much surface area. So probably that kind of experiment is not doable.
Yeah, actually, first of all, I'd say that it's not usually this kind of combination between platinum and nickel oxide, but considering the spin pumping process, I thought it seems to me that actually there is no net spin pumping going on, right? Because in ferromagnets spin pumping, actually we use the linear polarized microwave, so that does not really push any angular momentum in the system. So actually, that is because we're using a ferromagnetic field to keep this kind of orientation always there. So then you have a continuous spin pumping out of the ferromagnet. But here in antiferromagnet, there is no external field, right? So there is
there's an anisotropy field that gives rise to the resonance frequency.
So I just want to say that maybe it's not spin pumping, it's a sublet spin pumping, but overall it's not really kind of a net spin going on.
It's not a net spin pumping, but maybe it's a spin pumping from the two individual spin lattices the same. So eventually the spin current is cancelled.
Yeah.
That's why my question is, if you apply a magnetic field, the spin current will not be cancelled. So there will be an effective spin current coming in also in an antiferromagnet. This might be a way somehow to measure.
Okay, yeah, I try.
Yeah, you can still have spin current in that case, but provided you have circularly polarized antiferromagnetic modes, and that's the number question in nickel oxide. I believe there is a work that is being published where the authors, theory analysis, they claim that nickel oxide actually has a linear polarization. Don't give rise to spin. So you need a circular, you need right-handed or left-handed antiferromagnetic modes, chirality in the antiferromagnetic modes in order to get spin pumping. And that is an open question for nickel oxide because of the biaxial.
Another thing is that, so I think nickel oxide simply like this is not single crystal at all.
No.
So it's back to the.
It's a polycrystal.
You expect the new vector to be point to all kinds of directions.
All kinds of directions, yeah.
Do you think this would make the situation complicated or not for the analysis of the language?
So at least we just compare with the similar nickel oxide without the platinum. So we have a very a randomly oriented nickel oxide as a reference sample.
So this line sample with no big difference with the single platinum one?
Yeah.
I have one question regarding the animation first experience. So you perform the experiment on the sample with a 3 millimeter thickness, right? do you see the way how we can use the same technique for thin films? Thins means less than 1 micrometer. And how signal-to-noise ratio scales with the thickness? Is it like linear? Meaning like if you
I think it's a linear, right? So right now we have a 3 millimeter, we get this peak.
Yeah, so
and if you imagine, the volume of your...
You think there is no way we can use thin films, or can we somehow enhance this absorption by doing...
So we have all kinds of ideas, and we tested a lot of ideas, but so far, hasn't been working. So.
First of all, I would also support the comment that nickel oxide has this biaxial anisotropy, and from naive theory should have linearly polarized modes, which shouldn't contribute into the spin current. But on the other hand, what is the size of your sphere particle, and can you exclude that you have a surface magnetization which contributes to your signal? You see, so you excite some modes, some oscillations of the Néel vector, but due to this whole coupling of surface magnetization with the Néel vector, you can have spin current which originates simply from these non-compensated moments.
So it's a kind of, say, proximity effect? Means you get the induced moment in the platinum?
No, you can have surface. So if you cut your sample, you always have a non-compensated magnetization at the surface. You have this spherical particle. It's not ideal to play an interface or something.
For experimental, we cannot really see that. So yeah.
But can you have
So for your experiment with uranium thin films, have you checked the crystal structure of your actual thin films?
Crystal
It's
structure.
actually the first, not first, maybe the second product you have seen from the amount periphery is magnitude uranium.
Okay. I'm sorry?
It's highly textured films on magnesium.
Yeah, so it's L21 FCC. It's like a manganese 3 iridium crystal structure.
FCC, but in the same film,
FCC.
actually it's like distorted, or it has some textural string which actually change the crystal structure.
But it won't change the crystal structure. But there may be a strain, like a distortion. But we haven't characterized that. Yeah.
What the thickness of your film?
20 nanometers.
Yeah. So that means you haven't measured this outplane of the inplane that is constant yet, right?
No.
Okay. If you compare the inplane that is constant A with the outplane that is constant C, you will find they are unequal.
Yeah, sure.
That gives you this the triangle distortion which can break the cubic symmetry. That's why you see this loss effect. Otherwise, that switching field is huge because C.
So can you go back to the nickel oxide, the temperature dependence on the resonance? Because indeed you have a very good variation of frequency from 1 terahertz to 0.8.
Yeah.
As you increase temperature, frequency goes down.
Right.
So think about it. If you look at the width for a particular platinum composition, you'll find that you expect dynamical damping to increase with frequency, but to increase with temperature. But when you increase temperature, you actually decrease in frequency. So if you look at the evolution of your width as a function of temperature, you will just have to be able to tell whether this is combined. Right? Because if you increase frequency, you're expecting the dynamical damping to increase. As you increase temperature, actually you're decreasing frequency. But the thermal broadening should increase with temperature. You see things increasing, you associate that with thermal broadening. You see them decreasing, you will associate it with the spin pump.
Okay. Thank you very much for the comment.
I mean, it's true if the frequency goes higher, then of course the spin pump becomes larger, but on the other hand, at higher temperature, you may have a larger precession angle, which then would again increase the spin pump. Is it so simple to say straight ahead that the frequency increases?
But then you also have another harmonic which can also participate. 0.6 or Yeah, point one, yeah.
Question. What is the mechanism for the anomalous Hall effect in immediate magnetism here? And what kind of moments are switched by the magnetic field during your measurements?
Okay. Manganese. So it's very similar to the manganese 3 tin case, where we just switch a chirality of this triangle magnetic lattice. Yeah. And depending on this chirality switching, we can have the anomalous Hall resistance change.
Last question, be in time. No question anymore. Thank you.